Hello everybody, my name is Mark Spevick, and in this video I'll be showing you how to take this Hollywood style destruction effect a bit further with some advanced techniques that we can direct the effect a bit more. We will look at making some more interesting broken shapes as well as refining the impact. So let's pop over into Houdini. So here in Houdini we can see the simulation from last time, and the things I want to improve is basically the impact here. If we look at when the car impacts, it just hits the wall and the bricks just explode off. There's no sense of stretchiness or ductility in the wall to suggest that the bricks are glued or concreted together. They just kind of explode apart. The other thing I want to affect or get more control over is the overall shapes that we're seeing when the bricks collapse. We can, in a very rudimentary way, glue some of the bricks together into the shapes that we want, but ultimately I want to control or make more clumps of bricks and make some more interesting shapes. So let me show you some more advanced techniques in Houdini, how we can achieve our aims. I'm going to start by turning off the cache here, and I'm going to talk about the constraints first of all. Let's work on the actual impact. I'm going to dive inside the dot network here, and let's have a look at what's actually creating the glue, and that's this glue constraint relationship node. So this is defining our glue. Let's have a look at how that works. If I select this wall geometry, I can just turn off the display of the geometry, and then we'll just see our constraint network here, our glue. Now this is driven for the fact that there's a data name here called glue. If I change this name to something like Bob, then the constraint disappears. So where does this name come from? Let's dive over into SOPs and have a look. If we look in the wall network, if you remember, this side was our constraint network because that's where we painted the attributes. And if we come down the bottom here, you'll see there's an attribute create node. If you select this node, you'll see there is a constraint name. And that constraint name has a type here called glue. And you can see it appearing here, constraint name. And this is that name that we were looking for in DOPS. If I pop over to DOPS, this data name is that name. So there was nothing called Bob, but it was called glue. If I type glue back in, it reappears again. Now you can check what that is without having to go to SOPs by looking, if you remember, in the geometry spreadsheet. If you open up the relationships tab, you can see the name of all your glue relationships or constraint networks here. They have the same name as the node generally. And you can open that up and you'll see a constraint network drop down, but if you open that up, there's the geometry. Now you must remember to click on the correct class tab. We want primitives, so we'll click the primitive tab, and here are attributes, and there's the constraint name. So you can make sure you type the right thing in here, as long as it matches what's there. Now we can use this to our advantage. I'm just going to bypass or turn off this node by clicking on the little yellow flag there, and I'm going to hit tab. Now in constraint tools, you'll see we have a bunch of nodes with relationship at the end. Any of these nodes can be used in the way I'm about to show you. They can all be used with the relationships geometry. The one I want to look at is this new one for 17. It's called the Bullet Soft Constraint. This is like a spring constraint, but only better and a bit more stable. Let me plug that in. You'll see this is looking for data called soft. Let's call it glue. We already have a network with a name called glue, and there we go. This appears white. If we look in the guide options, there's the color. We can actually change the color if we want. If you really want. Let's make it obvious. Let's do it yellow. And I'm just going to up the stiffness to something like 1000 to make that stiffer. I'm going to display back my bricks again so we can see the effect of what's going on, and I'm going to press play. So now we haven't got glue holding these guys together. We've actually got this Bullet Soft Constraint, and this acts like a kind of a spring. So when this impacts, we'll see kind of a much nicer impact. They won't explode apart, but then we'll get some kind of stretchiness going on. So I'll just leave this go for a few frames. You can see the car's doing a nice impact. It's certainly stretching and things are holding together. Let me just stop that there. But it's not the effect that we want. But it's the impact I want. I like that bit, but I just don't like the rest of it. There is a slight problem. We can see the bottom of the wall is not attached to the floor. Let me just fix that first. If you remember, that was set because we had a group node in this wall geometry over here. Let me just move these guys out of the way. It was this group node here that decided which bricks were active and which weren't. And as you can see, the bottom is not selecting the bottom bricks. If I hit enter, I can just edit this interactively. Just pull up my bounding box and hit escape to come out of that mode. And now the bottom of that wall should be stuck to the floor in the sim. Excellent. So I'll just pause the video. No, I won't pause the video. We won't flipbook that. Let's just check very, very quickly to see if that sticks to the floor. Which I'm sure it will do on the frame of impact. There we go. Yep, that's all working. I like to be sure. So there's springs all the way through. If we hit W, we can see that they're those yellow colour all the way through. Now there's a slightly more sophisticated way of using this, and if you remember, we've lost our glue strengths that we've painted in as well, because there's no longer being judged by the glue. It's completely changed into the spring constraint. Now there's a slightly more sophisticated way of using the glue. Let me just explain how this works. I'm going to turn my glue back on. You'll see the data's called glue, and I'm going to return the change the data name back in the Bullet Soft Constraint back to soft. So we have our glue back on again. Let's go back to our wall network and then onto the constraints side, and let's find this attribute create node again. Now, as we saw before, we have this constraint name and it's set to glue. So this is what the constraints are going to be inside DOBS, because we have a constraint relationship node looking for primitives with this name. Now, for the glue only, there's a really nice feature that it has using another attribute. Let me click plus here and let's create this attribute. Here we can create our own attribute. Let's call this next constraint name. So the next constraint name is an attribute that's only used for the bullet constraints, the glue constraints. And basically, when the glue breaks, it's going to switch its constraint name from this to whatever we specify as the next constraint name. So in this case, we're going to set this to soft. So when the glue breaks, it's not going to disappear. Actually, it's going to switch into the soft constraint. The advantage of that is that the rest of the wall's glued, and it will keep our glue strength if we painted any of that in. Plus, we'll get a nice switch over on impact. So at the moment, this is we've created the attribute, but it's set to the class of points. We're dealing with primitives. We might change this to primitive. We can see it's appeared in the spreadsheet, but look, it's a number. That's because it's a float. Let's change this to a string, and that will let us type the word soft in. There we go. So when the glue breaks, it's going to switch to soft, the word, and we have a node here that's going to be soft. So if this is working now, what you should see is when you press play, when the impact occurs, the glue will break, but it won't just disappear this time. It will get switched automatically into the soft constraint. So hopefully we'll get our nice stretchy impact. If I hit W to see that in wireframe, and you can see there's our patch of where we painted our glue staying glued together, and the rest has become springs around that. So now we're getting the best of both worlds. Not quite the effect that we wanted. We don't want the sort of rubbery wall effect. We kind of want the soft constraints to break. Let me just flipbook that very, very fast, and then we'll see how that looks. So how are we going to get these soft constraints to break? Well, for that we need to look at a slightly more advanced technique in Houdini. Now, let's understand a bit more about how DOPS actually works. When we run a DOPS sim, on the first frame we do evaluate these nodes like we do in SOPs, and we populate the spreadsheet here with data. But as we go through every other frame, these nodes don't update the data or evaluate like in other contexts of Houdini. What actually happens is these solver nodes take the data in the spreadsheet, do what they need to do, work out everything in the scene, they re-update the data for the next frame, and we see our simulation occurring. Now, since this is Houdini, we can get in there and we can manipulate this data in between the frames and run that new data to the next frame, which allows us to control anything and everything as the simulation occurs. One of the easiest ways to do that is for the use of a SOP solver. Down here we have a SOP solver already attached to our relationship network. Let's dive inside and let's turn on this top node, and you'll see it's loading in our constraint network. I don't need this node, I'm just going to delete that for a minute. Now I'm just going to press play. The reason I'm pressing play is I want some of the glue now have changed into the soft constraints. The reason is that the soft constraints have different attributes to the glue constraints. In fact, all the different constraint types have some unique attributes to them, and it's some of the soft constraint attributes I want to manipulate. So now that's played through a little bit and we have some soft constraints. Let's have a look at what those constraints are. If I scroll across, we've got some interesting ones, things like torque and force. If you want to see a list of them all, you can click on the View tab here and see them all conveniently listed here for you. And we could use things like torque, strength, impact, force, angle to break our constraints. I'm going to actually use torque. Depending on the strength of the torque, which is a twisting motion, these are going to snap. So very quickly, I'll show you two ways of doing this. One is with the normal nodes, and the other one is with the wrangle. So let's. The first way I'm going to do it is actually group these up. So we'll group them based on the torque value, and then we'll delete the group, which is a traditional way of doing stuff in Houdini. And to do that, we can use a group expression node. So if you hit tab and type group expression, let's plug this in. This will make a group. Make sure that's set to primitives. That's the class we're dealing with. Let's call this delete me. And the expression is we want to refer to the torque here. If we have a look, it's a floating point number because it's got a decimal and it's got some rather large values. So we can do f at torque. So this will refer to that attribute. And we'll say larger than, let's do 1,000. So when the torque's larger than 1,000, it's going to group them up. And you can see it's grouped them up in yellow. We can then add a blast node to simply delete the group. Oh, there we go. Let's just wire that in. Let's move it a bit further away. There we go, and turn on the blast node. And you'll see the blast node's deleting everything, but we can specify the group at the top here, delete me, and it will only delete the members of that group. Now, that's a way to do it with just nodes. Another way to do it is with a wrangle node. Let's just do that for completeness. I'm going to, again, make a primitive wrangle because we're dealing with primitive attributes. Now, what I need to do here is just, first of all, I want to store the value of any primitive that's got a higher torque value than my threshold, and then I will delete that primitive, kind of similar in the way that we did it before. So we can store a value of the primitive number as an integer, so we can type int. We'll call this prim number, or prim no. And then how do we decide on the primitive number? We need to make a condition. So we can put the condition in parenthesis, and like we did before, we can say f at torque is larger than, and we can give it our threshold, let's say 1,000. We close the parenthesis. So that's our condition. If it's larger than that, and then we're going to put a question mark in, because we can say if this is true, do something. So if this is true, we can refer to the integer called prim num, or we can just return a -1. Now you put a colon in between the arguments and a semicolon to end the line of code. So basically, if this condition is true, we'll return the primitive number, which we'll store as this integer. And if it's false, we'll store a -1 in this integer. The reason we've done that is because we're going to use this other command called remove prim, which will remove a primitive. And we put a 0 in, which means the first input of the wrangle, which is the geometry that we want to deal with. We then tell it which primitive we want to delete. So we'll type in prim no here. So this will either delete the primitive number if it's over the threshold, or -1. There are no primitives called -1, so it won't do anything. And then we put a 1 at the end here, which means it won't just delete the primitive, it'll delete all the points associated with it. And you've got to put a semicolon at the end of that always, every end of line of code. And you can see it's having exactly the same effect. It's deleted the primitives which have over that threshold. If I bring the torque down to 100, you'll see it delete a lot more. If I put it back to 1,000, it'll delete a lot less. We can actually control this with a slider. We don't have to keep typing the number in the code, which is a bit awkward. It'd be nice to have a slider down here. We can do that with this command, chf. So chf, this will make a channel for us, and a channel that's a float, hence the f. And we can put parenthesis here, or the brackets. So inside here we give it the name of the channel. Let's just call this torque. Notice I've put the name in inverted commas. So there's the command there. It's not really working at the minute. until because we need a slider. So to make the slider is really handy. You can just click on this little button and that'll make the slider for you. When you click on this button, it looks through the code, it looks for any expression, channel expression, and if there is one, it makes the slider for you. And look, here we can adjust the number ourselves. So if we put in our 100 or our 500 or our 1000, we can see it's deleting less or more equivalents. Now interestingly, on the group expression here, you can do the same thing. So instead of putting the 1000 there, again we can type channel F CHF and then put our parenthesis and inverted commas. Then we can type in talk, close those off. And again, you'll notice the same little noggin here. If you click on that, you'll get your slider. And again, we can do 100 or 1000 or 500 or 1, whatever you want. Cool. So I'm going to leave my, oh, let's see the result of that one. Actually, we're not seeing the result of that one. There we go. So there's your 100. There's your 500. There's your 1000. I'm going to leave it on the wrangle one. So, yep, let's see the result of that. So now we've got, hopefully they're going to delete themselves when they've come over our talk threshold, which we left at 1000. So whereas before it was all stretchy, now on impact, we get our stretchy impact, and we'll see that some are breaking up. Some are not able to break up, and we get in these more interesting shapes, but not so many single bricks there. It's not so hard, easy to control sometimes, that one. Now if I dive back inside here, let's drop this threshold down to 500. Now it's a bit annoying diving inside and outside this network. A quick way you can keep these parameters for you is, if you've got a slider, that is, you can left drag the word into the viewport here. And look, you get a little slider. If I come up onto my .NET, the slider's still here. Now you can't edit the slider until you hit the special manipulator or this button here. And now we can adjust our value with our ladder, and we can change our talk value interactively without diving into the network. So there we go, we've made that a little less at 500. So again, we'll see some stretchiness at the first impact there, but then we'll see some bits staying together like we did before. And a few more broken up this time. There we go. A lot more single bricks. And the bit that we painted is staying stuck together there. So that's kind of a nice, interesting effect. What I'd like to do is add another layer of control. Again, we've seen how we can just paint the attributes here to keep our bricks together, and how we've used the constraints themselves, the talks, so some bits never broke apart, but that's a bit unpredictable. Let me show you a third way that we can control the way that this wall breaks up. I'm going to go back to the wall network and come right to the top to my original wall geometry. So let's have a look at see what this geometry actually is. Now there's a nice way to preview this geometry by hitting tab and type exploded view. If we drop that in and turn it on, we can see that this previews all our separate pieces apart from each other. You can adjust the scale, which brings them in and out. And we can see it is made up of a bunch of individual bricks. Now what I'd like to do is create or group these together without using the glue. And we can use, again, another new feature of Houdini 17. If you hit tab and type RBD cluster, we can create an RBD cluster node. Let me just plug that into my exploded view. And we'll see that it clusters together, or it groups together bunches of our bricks. Now this is very simple. It creates a point attribute called cluster, which you could make yourself, and anything with the same value gets treated as one chunk. Just going to turn off random detach for a minute so we can see the noise pattern. And it's basically a black and white noise pattern. And here we can adjust the size. So if we get big patterns, we get big chunks, or small numbers, we get small chunks. And if you play with them in their different axes, you can get some very interesting results. We can revert these back to the defaults very quickly by right-clicking on the word and choosing revert to defaults. In fact, let me just, oh yeah, and the random detach, we turn that on, just randomly detaches bricks. The higher you put that, the more it detaches. And the lower you put that, you can get some nice little bit of variation over the top of things there. Let's look for something like this. And I'm going to reduce my size. I only want sort of two groups, 3, 4 bricks. So let's keep reducing that down. Oh, something maybe 0.23, 24, 25, something like that. So we've got some nice clumps of a couple of bricks here and there, some nice shapes, and some single ones breaking off. Now, let me just connect that into these other branches. Now, there's a slight problem with doing this. Now that I've created these clusters, I've actually created a new constraint network for them. And since I've now created a new constraint network, my paint doesn't work anymore because it's all been shuffled up. So I'm going to have to repaint my my glue here, my glue strength. So I'm going to go to the background color and click Apply All. So everything's weak, and I'm going to go to the foreground. Don't forget to hit Enter to bring up your brush, and use Shift to scale the brush. I'm just going to again paint around the edges, like before, to keep those in place. Wanted to keep a little bit of that there. Let's keep our little blob of a brick section there that we wanted before. Let's see how this might look. Don't forget to turn on your dot import node so you can see the result of that here. And there we go. So I've painted my weights back in for the glue strength, and now we should see some of those clusters on the impact. We'll get a nice stretchy impact when the thing hits. Things break apart based on our torque, and there we go. We see some nice shapes based on those clusters, and there's the bit that we painted staying in the shape that we actually wanted. So we've got quite a lot of ways of controlling the breakup and the shapes here that we see on that impact. That looks quite nice and interesting. Much better impact than what we had originally. So there's one last thing. Have we got any intersections? Nope. There's one last layer of control again I'd like to add, and that is to if we have a look, we're getting whole bricks. We're not getting bits broken up. If a car does impact a wall, we'd see some of these bricks actually shatter and break. So let's add another layer of detail again. You know, we've got big chunks of bricks here that we've painted, smaller chunks we've used clusters for. Let's actually get some of these bricks to break on impact. We can actually use a shelf tool for this, and it's a really nice, useful one. If we go to the Rigid Body Shelf tab, we scroll across to the right here, you'll see we have Make Breakable. Make sure nothing is selected, click on Make Breakable, select your wall and hit Enter, and this will create a Voronoi Fracture Configure object node for you. Now I just want to change some settings here. The first one I want to change is this minimum volume. It basically voxelizes your chunks before it can scatter the points. If it doesn't work, make sure this is small enough that it does work. We also have a maximum and minimum impacts. Let me increase the maximum impact threshold up a lot, so even the most highest impacts will break these bricks. And let's see the effect of that. If I just press play, we can tell if it works, because as soon as it impacts, it'll go a bit slow. But what this will do, it'll interactively break some of the bricks, or procedurally break some of the bricks based on the forces, so we don't have to do much. There you go, that's taken a little second or two at the impact point, which is always a good sign. There's our stretchiness. If I just stop this for a second, we can turn on wireframe unshaded. This is great to preview actually your fractures. If I go back a little bit, there we go. You see at the point of impact all these fracture lines where these bricks have broken because the impact was higher than 50 and less than this number. If I go through again, we can see that we're getting some very interesting non-brick shapes where some have been shattered in half and some have been broken into a lot more interesting shapes. And that's breaking up some of our clusters as well. You can see all the constraints have got funky colors there. If you want to hide the display of them, you can select the glue wall node here and just turn off Show Guide Geometry. That will just hide them for us. So that looks kind of cool. What I'll do is I'll just pause the video while I play blast this, and then we'll see how that looks. So now the play blast is finished, we can see the impact of that. We can see a lot more detail, a lot more smaller pieces, bigger pieces. If I go through frame by frame, we get that nice sort of deform on the impact, and then a lot more control, and we can paint our glue strength and stop things breaking apart. And there's a lot more going on than before. So now that we're happy, like we did before, we can select our output node here, and we can just simply save that to disk and write the cache out. Since this is already cached up, that will write out very, very fast. And again, if you turn on initialize simulation ops, it'll ignore this cache and calculate it from scratch. To load our cache back in, we just simply turn on playback simulation. Let me just turn off the smooth preview and look through the actual render camera. And one last time, I'm just going to play blast that or flipbook that up using the cache, and we can see the full effect of our simulation. And we know that we can go back and we can change the overall pattern, the bricks that are left behind. We can change the chunks that fall out. We can change the different shapes that come through there, the big shapes, the small shapes, basically everything now. So hopefully you've enjoyed that video, and I will see you soon.